In this video, we are going to look at transfer learning for vision models. So the objective of this video would be to look at some of the concepts and intuition behind transfer learning and basics of layers. So in Keras, we define a layer and then what does it entail? So the properties of it, which are going to be useful when we are trying to use pre-trained models. So that comes to next one is how to pre-train, how to load pre-trained models such as a ResNet, exception, inception, and so on. And finally, we will look into dog versus cat end-to-end example. So first look at how we have been doing task learning or many machine learning models would do. So we have a data set with some labels. We will train and we will learn something about this particular data set, which are in circles, for example. And then that we get another kind of data set and we will train that one, and then we will learn, then we will use that for predictions. And then we will get another set of data set and we'll do the same thing again. So data sets that we get, which are slightly different, are used in different contexts, and we are learning different models. Whereas in the process of transfer learning, we are going to use few data sources and then combine them, and we will learn a model. And whatever the learning happens in this model, here I'm representing in knowledge, that is going to be useful for the next task that we are going to learn. So the next task will not be looked at in isolation, but it also has something that was learned before, which has some common characteristics of this particular model prediction. So another good example to look at is, like, let's say we have a data from many groups, and there are probably like one major group and then few minor groups. And if you try to learn a model, it will try to the model will perform very well in the major group but performs poorly on the minor groups. So the other option is, like, you can take a major group, learn a model, and you take individually minor groups here represented in red color, and then learn another model, yellow another model, and blue another model. So this way, but the performance is still poor in these models, even though these models are developed on its own data set. So the best way is to you learn from the major model, you learn some parameters, you learn some characteristics about the data set, and use that knowledge into learning other minority group models. So that's exactly what is being done here. So essentially, the learning that happened on previous but somewhat related data sets are being used to learn a new model, so it won't start afresh. So in case of images, what we usually have seen is that we have some data set, and we have been training using convolutional neural network, where a lot of earlier layers are used for feature extraction, and then the last layers are essentially we flatten and create a dense layer, and we create an output layer, and that particular is used for classification purposes. But all of these features are more or less common for all of the images. I can explain in images a little bit later, but I also think of it like if you have some problem where date is a variable, so you can extract it into hour, week, month, weekdays, weekends, quarters, and so on. So whether or not you go into any other data set, all of these are going to be the same feature. So that kind of features, if you're able to extract for any date feature, that will be useful, right? So that in a way, for images you have a lot more to do. For example, let's look at this. So if you have an image, in the earlier images you will learn like edges and shapes, edges, perhaps horizontal, vertical, and various kinds of edges. In the later layer you're learning shapes. So let's look at little bit more detail this concept of what is learned. So for example, in layer 1, if you look at this one, it is learning different kinds of uh, vertical or horizontal or slanted edges. So the first layer is learning edges. The second layer, if you look at it, so these are the true images, and it is learning, for example, circles. It's learning curves. It's learning different kinds of shape, but still primitive. But if you go into slightly more third layer, for example, you can see this is a net. It's encompassing somewhat primitive, and it's making a composite of those primitive, but still it's not the entire object itself, but it's learning slightly more complex in the layer 3, and so on. So in layer 4 and 5, it's learning a lot more complex shapes. So you can see, for example, you can take a dog. It is looking is somewhat a similar shape, so it's able to identify a dog shape, but it is made up of whatever it has been learned in the previous layers. So the summary of all of these images is that, okay, we can learn features in the earlier layers, and those features are common to many sources of images. So you can see that some of the images are made of animals, some of them are cars, some of them are people, but these features, the edges, shapes, the primitive shapes, or the composite of those primitive shapes is identical or is similar across many image types. So whatever it's being learned here can be used in a later phase. So before going to transfer learning implementation, we can try to know that what is ImageNet. ImageNet is essentially a dataset that was introduced in 2010 into a competition. Today it contains more than 14 million images with 22,000 classes of objects, labeled objects and animals and scenes. For example, objects could be laptop, baseball, banana, umbrella, animals, a dog, cat, elephant, bird, etc. And scenes, whether it's a mountain, beach, city, and so on. So the image size that was used varied, but usually in image processing, you can either reduce it to 256 by 256 or 130 by 130, and you can train your models from this ImageNet dataset. But you can see it's a very big dataset, 4 million dataset. So you can learn a lot of these from these massive dataset. So now we are going to go through about a coding implementation part of it, but overall the transfer learning is that the things that have been learned on one dataset can be used in other. In case of images, the shapes, basic shapes, and the composite of those basic shapes can be used to learn about any kind of images. So that's a general idea. So for the code setup, usually I have a project, and then within that I have a data folder, notebooks folder, and images folders. And so we will now look at into Keras basics, a primitive layer object known as layer. So in this case, I have the input values coming are 4, and then I have one layer with 3 neurons. So if you can look at, if you say layer.weights, you can see that it has 2 weights, and then if you say how many of these are trainable, so 2 weights in the sense one is bias and the other one is weights. Trainable, all of these are trainable, which means that when we feed input data set, these weights are going to change based on the neural network architecture that we implemented. So in further, if you want to look at the weights, you can say layer.getWeights, and within that I have weights and biases. You can see my original weights are as shown here. So there are 3 neurons and 4 inputs, so you have weights for all of those. And then you look at the biases. Originally the biases are 0 because we just initialized. But if you want to change it, which I try to do it, you can change this, say the weights of the first particular row to 999. So I was able to just change it by assigning weights of 0 is equal to 99, and then I'm saying set weights. So this is how you can get weight, and then you can update weights by using set weights. So this is a basic manipulation, and the another update that we looked at is whether this layer is trainable or not. So trainable weights is 2. So when we say trainable, if you say trainable, this set trainable is equal to false, what happens, the weights are not going to change irrespective whatever you try to when you're trying to update it. So this is also known as like freezing the weights. So this is for a basic one layer, but we can try to look at one already pre-trained model. For example, ResNet 10, there are many pre-trained models. So if you go into this Keras application, you will see lots of pre-trained model like exception, VGG 1619, ResNet, and so on. All of these models are trained for ImageNet data. So these are all models that use images, and you can see the sizes that we played and the accuracy they obtained. Image data, top 1 accuracy and top 5 accuracy, and the number of parameters it uses, and so on. So we will try to load this particular model, and how to do that is fairly simple. There are actually examples. If you go into Keras applications and look at, there are examples on how to upload it. So in this case, I am going to upload a ResNet 50. So all I'm saying here is keras.application.resnet 50 and improve ResNet 50. So this is so I'm saying the weights are for ImageNet dataset. So that's it. I have a model that's already there. So before going to look at it, what can I do with this model? So let's see, this model is already trained, ready to go. So I downloaded a few images, 2 elephant images and 2 deer images. Let's see what happens when we try to predict it. So the prediction code is here. So prediction dot model.predictx. So if I pass in an image, the first set of few lines is to display the image, and then here I'm converting that image into a dimension of 224 by 224, and then I am passing it to this model.predictx, and that's it. And let's see. So this is one more code that it says decode predictions. So the results, once I get it, I am using this function decode. So it will display, and I'm saying top is equal to 3. That way it will show you top predictions. So in this case, I downloaded a random image of an elephant, and then I uploaded. So you can see that it predicted it as African elephant with 91% chance, and then Indian elephant with 0.05%, and then a tusker with 0.027. So which means it did a pretty good job. So I download another image of a small elephant, and it says 99% chance that this is a Indian elephant, and then tusker is 0.006 and African 001. These are the top 3 predictions, which is pretty good so far. So I then downloaded a deer and try to do the prediction. So it couldn't find anything in the deer category. It did find impala, 8.15 chance, and then I download another deer image, and it says hardy beast, but it says it's not so sure. It's about 56% sure that it's a hards beast, and about 37% sure that it's ibex. So definitely the ResNet model is not perfect, but it does give probabilities of what kind of animal it is. So let's go back and look at what this model contains, understand the model, how can we use this model for our use cases. So if you look at a model.summary, it will show you what are all the layers it has. You can see number of parameters, output shape that is coming in, and so on. So this is fairly straightforward. So if you want to print names and look at whether each layer is trainable or not, and what is the length of the weights. So you have a bias and weights. So for example, so I'm printing input layer, and what is the weights? We don't need any weights. We are using a convolution path. There is no need of weight. But for batch normalization and convolution, con.con1, it has weights and biases. Here it has 4 parameters, 2 of which are trainable and 2 of which are not trainable. So all of this is, you can see, is it trainable? Everything is true here, right? So which means that if you feed in new data set and you can upload or update these weights. Okay, so another way of looking at this particular ResNet architecture or any other architecture is to use this dictionary. So you can say get config, and you will get a ResNet config dictionary. So what the keys it has is name, layers, input layers, and output layer. So you can further look at here. For example, if you go within layer, there is a class name, and then within that you have input layer, and then there is another configuration within that which indicates what is the input shape, output shape, and so on. So a lot of the details about a model are given in this dictionary. So if you want to look at in the form of a dictionary, which is, I did a JSON dump, and you can see it here. The input layers are shown this way, and then layers, different kinds of layers. And then if you let me scroll down a little bit and see what else you have. Yeah, another parameter that's important is like whether this is trainable or not, and it says true, which means that we can update this the weights for that particular layer. So again, if you can iterate through this dictionary and list out the names of each layer using this resnet.layers.i. So having understood about a basic neuron weights, and then we can update, let's try to look at a end-to-end classification of images, cats versus dogs. So the first thing is I'm trying to do is to load this cats versus dog data set, which is already available in TensorFlow datasets. So I downloaded, so I'm saying here tf TensorFlow datasets.load cats versus dogs, and then I am giving a split variable, which is an array. I'm indicating here that about 40% will be training. It is essentially splitting into three groups, and I'm not using entirety of the data here. Essentially I'm using only 60% of the data available. So the first 40% is for training, the next 40 to 50% I'm using it for validation, and the next 50 to 60%, 10% is I'm using for test. So this is 10% of the data, this is 10% of the data, and this is 40% of the data, which I'm splitting as training, validation, and test. And you can see the number of samples here: 9,305, 2,226, and 2,000. And you can see what this particular data set contains. And there are some dogs, there are some cats, and then for the sake of running this model, you have to resize this data set into 150 by 150. So you can so to do the resizing part, you can essentially use train ds to use the map function, and you can map x and you can resize it to the specific size. So if you have your own custom images, I think this step is useful. So this is batching images. I don't want to go in detail about this one, but essentially I think it will try to create a group of 32 images or variables, so that when you are trying to predict, or when you're trying to train, it can easily feed, it can feed the data very quickly. So image data augmentation, again, we have seen in the previous videos. So you can do it through layers at random flip horizontal, layers at random rotation, or there are other ways of using image data generator, but this is using through layers option. So this one, for some reason, this particular option did not work on my GPU. It's actually an issue that's not resolved yet. If you search for it on Stack Overflow, it says that this issue is being worked upon. So at this time, it's still under progress. So I had to not use data augmentation with GPU. So let's look at how to tune the ResNet model for our purposes. So when we are loading the model, we are loading the base model, and we are saying the weights are ImageNet, and we are saying include top is equal to false. So the top is, what is top here? Like the last layer is actually the top layer, like the classifier layer or the output layer, usually the top. So we are saying the include top layers, you get me all of the parameters and weights and biases from the network except for the top layer. So the top layer, it's not using the top layer from that particular architecture. And then I'm saying base model dot trainable is equal to false. What this does is that it goes through all the 50 or 40 layers that ResNet 50 has, and then it will set value to false. So essentially, what happens is that if you try to train on this particular model, it won't update the model. So this is, which means that we are freezing the base model. And then the final, so we are specifying what the input dimensions are, and then I'm how to scale the input values. In this case, I'm dividing by 127 and then offsetting by -1. In this way, you get each of the values between -1 and +1, which is how ResNet and Inception and other data has been trained. So it is important to convert into the same format. So you loaded the base model, and then we are saying training is equal to false, and then you're adding two additional layers. One is you're adding a average pooling on the previous layer of the last layer, and then you are using a dense of 1. This is after the dropout, which is essentially whether it's a 0 or 1. So it will produce logits as out. It will generate a number. If it is a positive, it means 1. It's a negative, it's 0. So that's it. I mean, we just created a new model which encompasses our old ResNet model, but also we added two more models on top of it, and we removed the top layer, the last layer, and added two layers to it. So we are using the weights of ResNet except for these two, which is what we are training. So you can see the model here. I think this, let's see, yeah, I used exception model actually instead of ResNet. So, and that model is already like fixed, and then it has these many parameters, and I added a average pooling layer and a dropout layer, and then finally a dense layer which has 2049 values. So as usual, you can do model.compile, and I'm using epochs of 20 and history, and I'm loading those values into history. So one of the things that happened here was when I tried to run on a CPU, it took a long time. So I actually ran this model on a GPU, not in this notebook, but externally, and that particular value is loaded here again. And then I created a model, and I started running that model within this notebook. So it's quite useful if you're able to save your model as soon as it finishes the fit. So in this case, you can see the accuracy is 96.9%. So as usual, we can try to look at error analysis, but there are a few things that are important here. So when you say model.predict, it generates predictions, but the outputs are some numerical values like 9.0, 10.7, minus 7.0, and so on. So these are logits, but it's not saying whether it's a 1 or 0. So that's something that we need to convert. So this is what I did. Anything positive, we are converting, we are saying that it's a dog. Anything negative, we are saying it's a cat. So again, this we are trying to look at how it performs on this test data set, which we have not used in training. So the test data set, to extract data from test, the usual way is to just you create an array and then you extract y and call y.numpy, and then you extend. So this way you will have all the values for the training data set in true ys, and x data will be in true xs. So you're extracting x and y into regularly usable arrays. So when you look at confusion matrix, so it was able to classify about 96 point, close to 97% is the sum of these correct predictions, and it failed about 3% or so. So you can look at which of the values it has done, it was able to predict accurately. So here I'm saying that, okay, I created a data set called prediction results, where I passed in true ys and prediction, and I'm saying wherever the actual is not equal to prediction, I'm creating a data set called error data, and within that I'm saying error 1, where actual is equal to 1, which means what was predicted was 0. Actual is equal to 0, which means these are dogs and these are cats. And if you look at the actual images were that of dogs, but it predicted as cats, these are the some of the examples. So as you can see, this one is in a cat, and this one I can't say what this is. Actually, it doesn't look like a dog, but yeah, definitely it got confused with these images. I think this is too back in the background, so maybe that's the reason why it couldn't predict as a dog. And these are the images where the actual images is cat, but it couldn't say it was a cat. So it said it was a dog. So yeah, these are human eye can definitely recognize them as cats, but the model could not do it a good job. So what else can be done on this particular data set? So you can use various models, and you can create an ensemble of prediction ensemble model, where you take all of the predictions and vote which whether it's a dog in majority of the which of those models say it's a dog, and if it's a majority count, assign it as a dog, and so on. So definitely you can do more, run for more iterations. Here I just ran for 20 iterations. You can definitely do that for your own projects. So with this I will wrap up, but before that, let's summarize what we looked at today. So we looked at what is a learning task in general, and then what is a learning process in transfer learning, and what happens in the initial layers, that we can use those features that are done in the initial layers from one learning and then transfer it to some other project or from some other model. And we looked at what in images, what it learns in the initial layers, which is quite common to various kinds of images. And we looked at what is ImageNet data set, and then looked at what are the basics of a L1 neuron, and then how to manipulate the weights of a neuron. And then we loaded a pre-trained model. In this case, we loaded ResNet 50, and we tried to do prediction by loading some random images from internet, and it was able to do a good job on elephants, but not so much on deers. So we also looked at what are all the manipulations that can be done on a model layers, how to get layer names, layer weights, and how to uh, set weights and so on. We can also look at how to access through dictionary, get configuration dictionary, and finally we try to do an end-to-end project where we are trying to predict whether it's a cat or a dog. And then we used exception model where we said the input shape is 150 by 150. So when we are preparing the data set, we change the model to 150 150 as well. And we try to keep all of the layers frozen except for the last two layers where it's average pulling data and a dropout data. And then finally we trained it for 20 epochs, and the prediction accuracy within this particular there is a notebook you are seeing is 0.97, but in fact the model was actually done on outside of this notebook for the sake of quick results, and the data augmentation was not used, so the accuracy was about 96.9%. And we looked at how to look at where this model is making an error, and we looked at some examples where actual data is dog but it thought it was a cat, and here are the examples where the actual data is cats and the model thought it was a dog.